In standard quantum mechanics, we usually describe a system using a state vector, psi. This works perfectly when dealing with an isolated, perfectly known pure state. But isolated, perfectly known states are rare in the wild. Real systems interact with their environment, which means we have to account for variables like temperature, background noise, and statistical probabilities. We see this breakdown in specific experimental conditions. An atom might exist in a mixture of varying energy states, or a quantum computer's qubit might suffer decoherence from thermal noise. When we lack perfect information, the system is no longer represented by a single coherent wavefunction. It becomes a mixed state, a statistical ensemble of possible states. There is a strict physical distinction here. A quantum superposition involves uncertainty built directly into a single state. A mixture represents our own classical uncertainty about which definite state the system actually occupies. To handle classical and quantum uncertainty simultaneously, the mathematical machinery has to expand. The wave function has to be replaced by the density matrix. This matrix provides a complete description of any quantum system, covering perfectly isolated particles and messy real-world statistical mixtures. Consider a basic problem. You are handed a particle, and you are told there is a 50% chance of measuring its spin as up and a 50% chance of measuring it as down. Look at the first way this can happen. The particle could be in a coherent quantum superposition of up and down. Because these two components are part of a single wave function, they share a precise, fixed phase relationship. Now look at the second scenario. We have an ensemble where half the particles are prepared spin up and half are prepared spin down. In this mixture, every particle is definitely either up or down. We just don't know which one. There is no phase relationship linking the two states together. If you run an experiment sensitive to phase, the superposition will produce a measurable interference pattern. The statistical mixture will not. Two systems can yield the exact same 50-50 measurement probabilities in one setup, yet remain completely distinct physical realities. To track both realities mathematically, physicists use the density operator, denoted by ρ. For a perfectly known pure state, the operator is defined by taking the outer product of the state vector with itself. For an ensemble, we expand that definition. We sum the outer products of every possible state in the mixture. Each term in that sum is multiplied by a coefficient, p sub I. This represents the classical probability that a randomly selected particle from the ensemble is in that specific quantum state. Because these represent physical probabilities, the total sum of all p sub I coefficients must always equal exactly 1. By organizing states and their classical probabilities together, this single operator captures every piece of information required to calculate any measurable quantity of the system. When you express that operator using a specific set of basis states, it forms a square grid of numbers. That grid is the density matrix. Here is a 2x2 density matrix for a generic spin system. It is composed of diagonal and off-diagonal elements. The terms running down the main diagonal, ρ up up and ρ down down, are called populations. These tell you the absolute probability of finding the system in each specific basis state upon measurement. The elements outside the main diagonal, ρ up down and ρ down up, are the coherences. Coherences quantify the quantum phase relationship between those possible states. They track the capacity for quantum interference. We can now distinguish our two 50-50 spin scenarios perfectly. The pure superposition has non-zero off-diagonal elements. The classical mixture has zeros. Those off-diagonal elements are the strict mathematical signature of quantum behavior. The closer they are to zero, the more the system behaves like a classical object. Because off-diagonal elements dictate the physical nature of the state, we can use the matrix to run a definitive diagnostic. We calculate the trace, the sum of the diagonal elements of the density matrix squared. For a pure state, this value equals exactly 1. For a mixed state, it drops below 1. That value rarely stays at exactly 1 in a laboratory. Real quantum systems constantly interact with photons, gas molecules, and thermal vibrations in their environment. These interactions scramble the phase relationships. In the math, this causes the off-diagonal coherence terms to exponentially decay toward zero. This specific process is decoherence. Decoherence destroys the quantum superposition. If the system also loses energy to its environment, the diagonal population elements will change, a separate process called relaxation. By tracking how the individual cells of this matrix evolve, physicists can map exactly how a fragile quantum state degrades into a classical mixture. Once we have the density matrix, we can extract real-world measurements. The expectation value of any observable is found by multiplying the density matrix by the observable operator and taking the trace. To know what those measurements will be in the future, we need to know how the system evolves over time. And the Schrödinger equation only handles pure wave functions. For the density matrix, we use the Liouville von Neumann equation. The change in the matrix over time is driven by its commutator with the Hamiltonian. The commutator measures how two operators interact. If the density matrix and Hamiltonian commute, meaning their order of multiplication doesn't change the result, the rate of change is zero. This is why a system in thermal equilibrium remains stationary. Its density matrix commutes with the energy operator, freezing its macroscopic properties in place. This framework applies whether the system is an isolated, perfectly coherent atom or a messy, fluctuating thermal bath. The math holds in both regimes. This mathematical framework is the exact engine running underneath medical imaging technologies like MRI. An MRI machine works by manipulating the spin density matrices of countless hydrogen nuclei inside a human body, aligning their populations and coherences with precise radio frequency pulses. The same math is required to engineer a laser. To achieve a stable beam, physicists use the density matrix to balance the diagonal populations, creating a population inversion while driving the off-diagonal optical coherences. By taking the expectation value of the dipole moment across that entire ensemble, we extract the macroscopic polarization. That polarization dictates exactly how the material absorbs and emits light. Whether tracking isolated qubits or thermal molecules, the analytical approach is identical. The density matrix allows us to rigorously calculate what state a system is likely to occupy and precisely how coherently it quantum